In this video clip, we want to discuss wavelet analysis. Wavelets are used because none of the previous approaches that we've looked at when looking at time frequency analysis are really applicable to all types of signals. So the wavelet transform is just a different way to describe a waveform that changes over time when that waveform is divided into segments of scale. Now, wavelet analysis uses probing functions that are compact. In other words, they have a short time duration. And the probing family will basically consist of the same function at different scales. So this has become a little more clear when we look at some slides that illustrate different wavelets. Basically, the continuous wavelet transform is not unlike the short-term Fourier transform. So here's the short-term Fourier transform that we discussed last chapter, where we have this windowing function that basically shifts. So the Fourier transform is done, and it basically slides with a time delay. So we get out basically a frequency spectrum that changes over time. So it's a two-dimensional output in T and F. So if we wanted to generalize that, instead of this Fourier basis function with a sliding window, we basically could combine all of this into a single f of t minus tau, where the f of t minus tau is a family of functions, and the subscript m indicates which family member is present. And if we do that, then we would get out a function that is a transformed x of tau that's a function of both m, the family number, as well as t time. So here's an example or an illustration. This black curve is a wavelet function, and you notice it has a distinct shape. And then we're going to take that wavelet function and slide it across the waveform that we're investigating. A indicates how the wavelet function is scaled. So you notice when A is 1, the function is fatter. When A is 0.5, the function is skinnier or more compact in time. So basically, by changing A, we can change the shape of the wavelet function, and we're simply doing something very much like a correlation between the wavelet function and the waveform. So clearly, when the waveform looks like the wavelet function, we'll get a high value for the correlation at that point in time, and when it does not look like the wavelet function, we will not get a high correlation value. And so that correlation value might occur at different physical locations for different scales. So in the continuous wavelet transform, we write this in a very specific way. So W, A, and B is going to be our output. X of t is our function of time. A is our scaling factor. So we have this function psi, which is the wavelet function itself. We take its complex conjugate, and then we divide by the absolute value, the square root of the absolute value of A as a normalizing factor. So B is what actually performs the shift. So when we take the transform between this weighted normalized wavelet function that's been scaled and shifted, our output will be as a function of scale and shift. So B is going to be a time-like parameter, and A is going to be related to frequency. So here are some examples of different wavelet families and the impact of changing A. This particular wavelet family is known as the Morley wavelet, and it can be defined by the equation shown on the slide here. And so if we choose A to be 0.5, then basically we see that we have the following function. If A is 1, which is known as the mother wavelet, it's the basic wavelet form. We see the function here, and then notice as A gets larger, the function is being more dilated. So a larger value of A, the scaling factor, results in dilation of the wavelet function, while a smaller value of A results in compaction of the wavelet function. So notice that small values of A are higher in frequency. So scale has an inverse relationship to frequency. A small scale would reflect higher frequencies in the signal when we do the convolution, while a large scale is a lower frequency component of the signal. So in wavelets, there is a time frequency trade-off. So we're going to get, just because of the basic uncertainty principle, we're going to get either good resolution in the time domain or in the frequency domain. And so what we find is that the uncertainty in time and the uncertainty in frequency is a constant, and that constant is greater than or equal to 0.5. So we'll either have kind of a broad frequency range represented in our wavelet transform, or a broad time range represented in our wavelet transform. And that's going to be constant across scale. So we can look, if we use a function known as the Mexican hat, and A is varied, we can see that when A is larger, we're going to get good frequency resolution but relatively poor time resolution, while when A is smaller, we'll get relatively compact time resolution but rather poor frequency resolution. So here's an example, and this is not using the wavelet toolbox. MATLAB has a wavelet toolbox, and it's a good toolbox. But in this case, we're going to implement a wavelet transform basically using the correlation between two functions. We're going to plot the wavelet coefficients as functions of A and B using both a 3D and a contour plot form. And we're going to generate a signal that consists of two sequential sine waves of 10 hertz and 20 hertz. So it'll be 10 hertz for a while, and then it'll be 20 hertz. And here we're going to use the Morley wavelet. And on the Morley wavelet, you have to tell MATLAB how many points you want in your Morley wavelet, because it'll construct the wavelet for you. So you have to tell it how many points you want, and you have to give it a sampling frequency. And so in this particular case, when we generate the wavelet, we generate the positive half and then flip it so that we get the full wavelet. We generate the signal waveform just in a standard way. And then we're going to choose the range of A beginning at 0.25 and then decreasing. So we actually aren't using the mother wavelet in this analysis. Now, let me go back, because this is a little bit of a judgment call, and sometimes you have to play around with what you want your value of A to be in order to get good representation of your signal. So, we might have a different experiment where we wanted to range A from 0.25 to 10. It just depends on your application, and sometimes it's a little bit of trial and error to get a feeling for your data. So here's the code. We first set up all of our constants. So here are our frequencies. Here's our signal length and our half wavelet length. Here's our sample frequency. Here's our resolution level. In other words, how many levels do we want to decompose into? And here the author selected 120. And then decrement for A just means as you shift the scale, what do you want the delta to be? And then we're going to initialize A at 0.5. And then this is the frequency, the fundamental frequency that's been scaled with a log scale. And then here's the time vector for the wavelet and plotting. So we're going to generate a time vector based on our sampling frequency, and then we're going to generate the function showing that we have one frequency for a certain time duration and then another frequency for the same time duration. And then we'll calculate the continuous wavelet transform. So this comment is incorrect. On the previous page, the author actually set the resolution level to be 120. So we're going to start with level 1, and we're going to go to level 120. And then we're going to start with that initial value of A, which was 0.25, and then basically in increments of 1 plus this decrement level, which is what's going to divide it into 128 levels, we're then going to scale. The time vector for the wavelet is then scaled, and the Morley wavelet is constructed using the equation, the positive part of the equation, and then it's made symmetrical by doing a flip left right and then constructing an array that's the flipped wavelet as well as the positive part of the wavelet. We then convolve the flipped wavelet with our signal, and we then look at how much we actually have in the signal. We look at the length and basically remove any extra points. Now, why would you have extra points? You have extra points because when you flip the wavelet and make it symmetrical, basically you've got twice the length. So you have a data array of 1,000 points that's being convolved with a wavelet that's most likely 2,001 points because you've doubled it and you've made it symmetric about 0. So you have to remove those extra points and divide the length by 2 so that you can get the unique part of the convolution. And so then the wavelet transform is given here. And the extra points are removed. So here's the result. You can then do a contour plot of the value of that wavelet transform, which is basically the value of the convolution, with B, the shift, and A, the scale. So here we're going to show a contour plot and a mesh 3D plot. So here's the original signal up here in the top left. And you can see midway through at 1 second, the frequency abruptly changes. So here's the continuous wavelet transform. A is scale, and remember, higher scale is lower frequency. So this low frequency part of the wave shows up at a scale peaking at about 0.8. And then the higher frequency is going to peak down at about 0.4. Once again, your author has a typo in his slide. This is actually a 10 and 20 hertz signal. And notice that the scale does indeed have when you go from 10 to 20. Notice that the time scale is different because remember when we scale that for the wavelet, we get, so you have to be really careful here because you notice our time scale runs from 0 to 5 here in seconds, and our time scale here runs from 0 to 1. So what you get out is not necessarily a one-to-one correlation with the time. Notice you have quite a bit of time here before you actually pick anything up. And then you have time here after the second part of that signal is gone. So the wavelet has like a finite duration. If we were to go back and look at the wavelet function itself, may not have a good plot of the Morley wavelet. Now it's kind of similar to this. You notice that for this lower scale, the wavelet's getting really compact. And so there's a lot of space here where the wavelet's value is 0 or close to 0. So that's reflected or illustrated in the fact that you have this sort of dead space before the actual signal starts to show up and after it's over, even though in the original signal had such space. This one was rectangularly windowed and padded a little bit, so you do get things here. Now you want to do that when you do a wavelet transform because of the way the wavelet has that kind of that long space between when the analysis starts or when the window starts and when the wavelet actually appears. You want to include some space here as well because you want when the wavelet begins to overlap the signal, you want the entire wavelet to be in this window. So that's more of a MATLAB trick than a mathematical one. In being able to pull out features from your signal. Here's what the 3D plot looks like. You can see that you do get a finite width here. So what this means is that this frequency is picked up by multiple scales of wavelet. So, for example, in this frequency, which is 10 hertz, or this is the 20 hertz, I believe. So in the 20 hertz frequency, you can see that you start picking up some non-zero values really at a fairly high scale. And then you do get this peak at a scale of about 0.04. And so you get a peak there, but in the scale of 0.1, notice we still have a pretty significant non-zero value. So this is a redundancy that exists in wavelets, and the reason for the redundancy is that the frequency spectrum of a wavelet is broad. So if you were to do a frequency analysis of this wavelet we've used, you would find it's not a single frequency component. It actually contains multiple components. And so because of that, you do get some redundant information in the continuous wavelet transform.